time constraint. Yes. Next speaker is Professor N.D. Haridas. He's also going to talk about weak values. Can weak measurements restore the validity of the individual in quantum mechanics? Professor Haridas.
Yeah. I'm grateful for that opportunity. And I would like to wish Professor Leggett somewhat differently than what others have been doing. For some of us in India, 80 years in itself is not so special, but 80 years, 10 months, and a week is very special. You may wonder where this strange combination of years and months comes. It turns out to be the time that passes with 1,000 full moons. So this is called the Sahasra Chandra Darshana Yoga. So I would like to wish you another 1,000 full moons. So I want to talk about this provocative title, Can Weak Measurements Restore the Sanctity of the Individual? I will explain what I mean by this. But let me make a clarification that the weak measurements I'm using here, the same phrase is often used for what should correctly be called the weak value measurement. This is not a weak value measurement. This is weak measurements, as Aharnov had introduced, as a prelude to the concept of weak value measurements. Okay, now one of the most dramatic aspects of quantum mechanics is what at least I call the demise of the individual. More precisely stated, it says that no information can be obtained about an unknown state of a single copy. This is a straightforward consequence of projective or strong measurements and the principle of superposition. There's not much we can do about principle of superposition, at least right now. But as far as projective measurements are concerned, we have now a variety of quantum measurements which we can substitute for projective measurements. And the reason why this happens is very clear, because the first measurement randomly results in an eigenstate, and any subsequent measurements on that has no bearing on the original unknown state. So the weak measurements offer a superficial hope that it may be possible to determine the unknown state of a single copy, and the basis for that hope is that each weak measurement with high probability very weakly alters the system while giving some information. So the question is, can we gather all this information and determine the original state? I may mention that this demise of the individual, I hope leftists don't take undue advantage of it by claiming superiority of the state over the individual. There is a peculiar consistency, because this argument was based on measurement aspects of quantum theory, but there's also something called the no-cloning theorem, which says there is no universal cloning possible of quantum states. If universal cloning was possible, then even with a single copy, you could have produced a large ensemble and used that ensemble to determine the state, and you would have, the individual would have got resurrected. These are two orthogonal aspects of quantum mechanics, because the no-cloning theorem follows purely from the unitary evolution aspects, whereas the first argument came from measurement, and there is this unsuspected consistency, and this, at least for me, is something that one has to understand in a better way. A very quick introduction to quantum measurements. So we have a system in which a measurement has to be performed, and in some given state, and some observable has to be measured, and we invoke an appropriate apparatus, and first we introduce an interaction between the system and the apparatus, which, by the way, is a unitary evolution. Often in many presentations, this is confused with the actual act of measurement, which it is not, because this is a unitary evolution. And then we have to sort of specify certain states of the apparatus which are called the pointer states. And these are determined by appropriate apparatus-environment interaction if you follow the decoherence picture, whether decoherence is really what's happening in quantum measurements or whether it is just, the quantum emperor's clothes. We don't know. And it will be very interesting if in the discussion session we can spend a little bit of time, as to what exactly one should make of the decoherence picture for quantum measurement. And this decoherence is brought about by a different kind of interaction, which is a system, by an environment apparatus interaction, whereas the measurement interaction is system apparatus, and a priori these are not related to each other. They could be quite independent. So again, a quick introduction to the projective measurement. So suppose, we have some pointer state here, and we introduce a measurement interaction. If it's a qubit, then if it's up, the pointer state is shifted right, and if it is down, it is shifted to the left. And if you take any general superposition of states, linearity of quantum mechanics tells that upon measurement interaction, you go into this entangled state where the P plus state of the apparatus is correlated with the upspin, and likewise P minus with the downspin. And so far, everything is fine, but what we should do later depends on one's point of view. Decoherence attitude says, take this density matrix and drop all the off-diagonal terms. And so this is supposed to be the final density matrix that results after complete measurement. And this is clearly a mixed state, and its purity differs from the ideal purity of 1. So the reduced density matrix after this decoherence interaction looks like this. So this is just to provide a framework for what I'm going to talk about. Now I talk about weak measurements, and for sake of definiteness, I take the pointer variable of the apparatus to be a momentum variable. And now the pointer states are taken to be momentum eigenstates. Of course, the continuous variable, there are all kinds of difficulties with that. So in practice, these are taken to be narrow Gaussian packets in momentum representation. The only difference, there are many ways of motivating weak measurements. One is to say the measurement interaction is weak, but that is not really necessary. You can use the same measurement interaction in weak and strong measurements, provided you change the initial state of the apparatus to be a broad superposition of pointer states instead of a pointer state itself. These two are equivalent, and I will choose this characterization of weak measurement. So my apparatus state is really a broad superposition of pointer states. Measurement interaction, as I said, is taken to be the same as in strong measurements. So this is like a von Neumann-like model for weak measurements. Von Neumann model, of course, has a lot of defects, but for nothing better is available, so we just use that. So the initial system state is, this is some observable A, these are the eigenstates, and it is taken to be a superposition of those states. Now the post-measurement interaction state, that means after the measurement interaction, which is unitary, then the state looks like this. So all we have done is the interaction has shifted the pointer state of the apparatus by the eigenvalue. Now this can be rewritten in the following way, where we just shift the variable from P plus AI to P, and that transfers it there. And you can introduce a new state which is obtained from the old one like this, and NP and the parameters of the initial state is an expression like this. So this is just rewriting that entangled state in a more convenient way. You can also view the this kind of weak measurements as a positive operator valued measurement, this is just a technical remark. I'm not really going to make use of this. Now, the post-decoherent state is you take the density matrix of this and drop all the off-diagonal entries in the pointer basis, and this is what you get. So now we interpret this as the probability distribution for the pointer outcomes is this, and if the pointer outcome is P, then the system state is psi P. So unlike strong measurements where a pointer state is only correlated with an eigenstate of the system, here a pointer value P is not correlated with any eigenvalues. Nevertheless, there is a collapse. This is not correct to say that in weak measurements there is no collapse, but the collapse is not to the eigenstates of the observable. That's all. So now we have since what is going to be measured are the outcomes of the apparatus, let us carry out some analysis of the statistics. So the average value of the pointer position, you can immediately work it out from this, and that turns out to be just the expectation value of the observable in the system state. And if you take the variance in the pointer position, that is that width of the apparatus Gaussian plus the variance in the system, but weak measurement means this number is very, very large. Therefore, the system variance almost plays no role at all. Now, this is how you would interpret an ensemble of weak measurements. That means you have an identically prepared ensemble of states, and on each one of them you make these weak measurements, and P's are the outcomes, and you carry out this analysis. Now, the reduced density matrix also can be worked out. Just mentally make note of it. Now, what I would like to understand is that was for an ensemble. Now, I have a single copy of an unknown state. The previous picture with projective measurements was that had no statistical significance. But now, suppose we make repeated weak measurements on a single copy. So the schema is you make a weak measurement of an observable A. This is an unknown state, single copy. Note the apparatus outcome, let's say it's P1. Now the system state has become that psi of P1. Restore the apparatus to the original state before the first weak measurement. Perform the weak measurement again, and now you get an outcome P2. The system state goes to psi P2, etc., etc. You go on repeating it. Now the big question is, does the statistics of the outcomes, P1, P2, Pn, have anything to say about the original unknown state psi? So it's a well-posed question to which the answer has to be one way or the other. So let us work this. The probability P1 of the first outcome is given by that. System has gone to psi P1. Now this is a map from the initial state to the psi P1, and it is useful to think of this as the change value of this. There has to be an alpha I here, I'm sorry. So starting with alpha I, you go to alpha I1 after the first stage of measurement. The probability P2 of the second measurement, which is conditional to getting P1 in the first measurement, can be worked out. And this is a conditional probability. And it looks complicated because there's a denominator there. But if you work out the joint probability distribution, that looks beautiful. The denominator goes away. You basically use the Bayes theorem to compute the joint probability. And after those two measurements, the system has become this. And you can immediately generalize this to any number of measurements. And the joint probability distribution looks like that. And the system has gone in. So the system is actually doing a random walk in state space. And the apparatus is also doing a random walk, in terms of the outcomes.
I'm slightly confused. If you don't do the original state, how do you restore it to the original state to do the second calculation?
Pardon?
If you do not know what the original state
Yeah.
is, how do you restore it after the first
No, only the apparatus. You don't restore the system. Apparatus, you know, you started with a well-known state of the apparatus. So you only restore the apparatus so that you make a measurement under the same conditions. That's all.
Weak measurement is after all the measurements. So it will discuss slightly.
Can we discuss this? Because chairman is waiting with his hand in the guillotine. So now these codify all the information that we want, and therefore we can answer this question in a fairly rigorous mathematical manner. The joint probability distribution is not factorizable, but it is because the second measurement depends on the outcome of the first measurement, so they are not independent, but nevertheless it is of the so-called separable form, and that is what is important for us. Now I compute the average ym of m outcomes, which is simply p1 plus p2 plus pm divided by m. It's very easy to compute this, and you again get the average of the observable in the system state. So you may think, well, we have obtained full information on the initial state, so we could determine it, but this is illusory because we have to analyze that result a little bit better. So for that, we look at the distribution function of ym, which can also be calculated in a straightforward way. Remember, in the case of ensemble measurements, this distribution function for the average is the central limit theorem, and it says that this ym will be peaked around the true average, whereas in weak measurements, the story is completely different, because in order to get the central limit theorem, the probability distributions have to be independent, and here they are not. They are conditional upon each other, and so the central limit theorem does not follow, but instead you get something equally transparent, that the probability distribution for the averages is actually a sum of central limit like theorems, where the averages are not centered about the true average, but around various eigenvalues. And that's a very important and central difference. So it's a weighted sum of distributions that increasingly peak around the eigenvalues as m increases. In the limiting case, the averages over a particular realization. By particular realization, I mean you got a sequence of p's that comes upon performing on this single copy. Now, if you repeat this on the same unknown copy, you will get a different sequence, and that will be a different realization. So averages over any particular realization, they only give information about the eigenvalues, and therefore they do not give any information about the state. So the state cannot be determined by doing these repeated weak values. So here is a picture. So think of all these different realizations. You can think of, they're all kind of random walks in system space, and likewise a description for the apparatus also. So what this is telling us is that as you keep on making weak measurements, they will start hovering around the eigenvectors of the observable, and some of them go near that, and some of them will go like that. So this map from one point to another is a map in state space, and it's easy to see that the eigenstates are the fixed points of this map. So if you start with an eigenstate, you just step it, and you can't go anywhere. But if you start with any generic state, you can't exactly go into the eigenstate, but you can come arbitrarily close to it. And the fact that the distribution is a sum centered around the eigenvalue, very close to it, means that each trajectory spends a lot of time in the vicinity of this eigenvector, so it keeps on simply adding up that eigenvalue large number of times, so the average becomes the eigenvalue itself. Okay? So another way of stating this is that this history can be labeled by one of the eigenvalues. So now we make a comparison which brings out in a transparent way the difference between projective measurements and weak measurements. In strong measurements, each outcome is in 1-1 correspondence with the eigenvalues and eigenvectors, and different outcomes occur with probabilities as given by the Born rule. On a single copy of an unknown state, the projective measurements can only give information on the possible eigenvalues, but if you make an ensemble of measurements with sufficient number of observables, you can actually determine the unknown state. Yes. Now, in contrast, in weak measurements, the outcomes of the apparatus are weakly correlated with the resulting system state. Repeated weak measurements give histories instead of definite eigenstates. Each history occurs with a probability again governed by the same Born rule. So that is the simplified picture one gets. And since time is running out, let me quickly run through some results. You can likewise compute the average of the reduced density matrix. So in other words, the weak measurements, when repeated very large number of times, they just become identical with a strong measurement. So there are other aspects which we can probe. If you compute the average of the system density matrix, this is what you get, where m is the number of measurements, and in the limit m goes to infinity, this just becomes a reduced density matrix in a projective measurement. In the limit m goes to infinity, the off-diagonal part of the density matrix get completely quenched, as in decoherence, but this decoherence is different from environment-induced decoherence. This is just a decoherence induced by the measurement process itself. And such an effect was also noted by Gurwitz long ago. I think can't give any more details of this due to lack of time. You can get an error disturbance relation. So if epsilon is the error and d is the disturbance, then you can get a relationship like this. So reducing errors can only be at the cost of increasing invasiveness of this weak measurement. So here are some references, and such an analysis was also done by Alter and Yamamoto long ago. They used weak QND measurement, and their observables were continuous observables, and therefore in this picture of the landscape of eigenvectors is not very clear because the fixed points completely cover the space and it is not very transparent. Whereas what I have done is for a observable belonging to a finite dimensional Hilbert space, even though the apparatus used is a continuous variable Hilbert space. Thank you very much.
Thank you. Any questions or comments?
I'm a little hard of hearing, therefore, if I give answer to a question you didn't ask, please forgive me.
So is this evolution somewhat akin to the Zeno effect with the following difference, that in the Zeno effect, by repeated strong measurements, you are actually restraining the system from
there
evolution?
is akin to Zeno effect only in the sense that you're performing repeated
but
measurements.
in this case, weak measurements.
That's
but
right.
in this case, you can say that
But
rather
however, the Zeno effect can also be analyzed by repeated weak measurements, and there is some conclusion by Alter and Yamamoto on that.